Hi thinkers, welcome to the Data Structures in Python course on ThinkX Academy. In this tutorial, we are going to cover a very important algorithm which is the Bellman Ford Shortest Path algorithm. So first things first, I'm going to show you the whole conceptual idea behind the Bellman Ford algorithm, and we are also going to implement this algorithm in Python programming also. So here you can see we are going to write the whole program here, but let's first start with some of the very important things about Bellman Ford algorithm and why do we need this algorithm. So first of all, in this playlist we have already studied Dijkstra's algorithm. Now Dijkstra's algorithm is already there to find the shortest path of a particular given graph. So why do we need Bellman Ford algorithm? So the first thing is that there are possibilities that a graph may contain negative weights, right? So it is possibility that a graph may contain some negative weights, and this is the main reason why Bellman Ford algorithm is useful, because Dijkstra's algorithm will fail in cases when a graph has some negative weight. So let's say there is a graph which has nodes like this. Let's say there are these three nodes, and let's say the cost is -2, 1 and 10. So in this case you can see the edges having a negative weight, so the Dijkstra's algorithm may not be able to find the shortest path in such a case. So Bellman Ford algorithm is going to solve that thing. So that's the first reason why we are studying Bellman Ford algorithm. The second thing that you will ask yourself is, what are the applications of such type of cases? Why do we have such type of graphs with negative weights? Now the answer to that question is very simple. There are some cases, some real life applications where you will encounter some of the applications of graphs with negative weight. The first example is chemical reactions, right? So let's suppose there is a chemical reaction. In the chemical reactions, heat is absorbed and heat is released, right? So heat is involved here. Heat is sometimes absorbed and sometimes it is released inside of a chemical reaction. So if we want a graph to represent all the sub reactions and all the chemical reactions, and there is we are studying the heat diagram and the heat is released, so in that case we are not able to find out the shortest path. And then we have one more important, which is the money transactions. So we may encounter a problem where we want to actually depict a transactional diagram of a particular graph, and we know that cash will the money will go into the one node and will also get withdrawn. So in that case negative weights are very useful. There are more such applications. There are so many applications of using negative weights inside of a graph. Now with that, we want to now write an algorithm to actually solve this case of this Bellman this shortest path in the negative weights. So the first thing first is, are there any disadvantages of this algorithm? We will also discuss. The first disadvantage of this algorithm is that it is it is a lot slower than Dijkstra's algorithm. So I'm going to write here that it is indeed it is slower than the Dijkstra's algorithm. We know that the Dijkstra's algorithm, we have already studied the whole tutorial and we have also implemented the Dijkstra's algorithm in Python also, and we know that Dijkstra's algorithm at each and every step uses a priority queue. It uses a priority queue or a heap to actually use and find out the element which is the minimum of all, and then it starts exploring and makes adjustments to the cost. We all know that. Now this is a greedy approach. We can say that this is a greedy approach because at each and every step the Dijkstra's algorithm tries to find out the minimum element of all the neighbors, right? Now Bellman Ford algorithm is not a greedy approach. Instead, it is a dynamic programming approach. right? So I'm going to write here that it is instead a dynamic programming approach. Now in dynamic programming, what we actually do is we actually try to find some results of some sub problems and we store them, and then we can use them later. So we actually try to store the results of sub problems, right? So this is basically dynamic programming, and you will see in a later, when we will move in with the tutorial, you will see how dynamic programming is used in this algorithm. So with that, now let's start with the algorithm. Let's start with an example first. So here I'm going to take an example of a graph. So we are going to have 6 nodes here. The first node is A, the second node is B here, and here we have C, D, E and F. Alright, that's the first thing. The second thing, that this graph is a directed graph. It is a directed graph, it is not an undirected graph, and this is an important thing, that the Bellman Ford algorithm will not work in undirected graphs. Here we have a directed graph, so from A to B I'm going to show a direction here, that if you go from A to B, the cost that will take is 6, so the weight of this edge is 6. Then we have some more edges here. I'm going to draw some more directions, and these are actually the edges of this graph. The weights are 4 and 5 here, and then D is connected to C, and the distance here is -2. C is connected to B, and the distance is again -2. B is connected to E, distance -1. C is also connected to E here, right? So here C is also connected to E, the distance is 3, and then we have 2 more edges. One is going from D to F, and this is actually -1, and then we have the final one, which is E to F, and this distance is actually 3. Alright, so we have this graph. Let's say this is graph G, and this is the example that we are going to use in the tutorial. So the first thing I'm going to do here is, in Python, since I know the problem, first I'm going to write the problem here. So you can see that this line number 6 is the main function. Here I'm actually trying to create a dictionary which is graph, and it is a representation of this graph. So you can see here that in the keys I have all these nodes A, B, C, D, E, F, and it is kind of similar to what we have implemented in the Dijkstra's algorithm also. This is the same thing. So A is connected to B, right? So you can see this is a dictionary of dictionary. So graph is a dictionary here, and this is a dictionary of dictionary. So A is the key, and the neighbors of A are here, right? So A is connected to B, and the value here 6 represents the cost or the weight of the edge. So you can see A is connected to B and the distance is 6, so I've written 6 here. Similarly 4, 5 and all these distances is a representation of this, and since we know F is not connected to any single vertex, so I'm going to make sure that it is empty. Now remember, it is a directed graph, so A is connected to B, so you can see here A is connected to B and it has a cost 6, but B is not connected to A. You can see that we don't have any direction, so inside of B you are not going to write a entry of A, right? You're not going to do that because this is an example of the directed graph. Now we have a source, and source we are taking in this example A is the source, and you can take any destination E. Now one important thing about the Bellman Ford is, what it tries to achieve is, let's say we are given a source, so A is actually the source, I'm going to mark it as S. So the Bellman Ford algorithm will actually find out the shortest distance from this source to all the vertices, right? So if I want to find out what is the shortest distance between A and E, the algorithm will find out that also, and it actually computes at the end of the algorithm the shortest distance is actually the cost which will be assigned to these vertices. So that's an interesting thing. We can run the algorithm once and we are actually able to find out the shortest distance to each of these elements, right? So now let's start with the first step of this algorithm and try to understand how it is different from the Dijkstra's algorithm. Now in the Dijkstra's algorithm, we know that we will assign the cost of source as 0 because it takes 0 efforts to reach A, but all the other nodes will have a cost infinite, right? So C will have a cost infinite and all of these vertices will have a cost of infinite. What does infinite means? Infinite means that we can actually track which of these vertices have not been visited. So actually they are not explored. So if they are not explored, it means that the distance, the cost that it will take from the source A to reach that node B is actually infinite. So we are going to take the step 1, which is assign source as 0 and all the other nodes should have a cost of infinite, right? And I'm going to do the same here also. So inside of this function Bellman Ford, I'm giving it this dictionary graph, this source and destination. So I'm going to first create a infinite value which we can get from sys.maxSize by importing sys. So this is the infinite value. Now I'm going to create a node data which is a dictionary, and this node data is actually representing the data of every node. So every node will have two things. The first is the cost and the second is the set of predecessors, which is actually a list, right? So these are the two things that each and every node inside of this graph will have. So that's why I'm creating a dictionary node data that keeps the track of each and every node, the cost and the predecessors of each and every node, right? So that's what I'm doing here. I've created a node data dictionary. See, I have written here that the first node is A and it has a cost as infinite and the predecessors are empty here, right? I will do that with B also. So B has a cost of infinite and predecessors are none. Then we have the C also, and then we have D, E, F, and that's all, right? So here we have assigned the cost of all of the nodes as infinite and the predecessors list is empty. So whenever we are going to assign the cost or make changes to the cost, we are also going to make changes to the predecessors. Now we are going to assign the cost of source as 0, right? So we are going to say node data source. So there are two indices. The first index is actually going to represent the node name. So the source is actually A here. So now it is representing A. The cost is 0. So this infinite value will get assigned to 0, right? That's the first step. Now we are going, before moving to the next steps, let's now try to understand the step 2, which is how this algorithm is going to compute all the results, right? So the idea of the Bellman Ford Shortest Path algorithm is pick a node, right? Starting from the source node, you pick a node and you assign the cost of all the neighbors of that node. You try to do adjustments of the all the corresponding nodes, right? Now the question is how we are going to do that. Now we are going to use a very simple adjustment formula. So some people also say they are it as a relaxation formula. So I'm going to write here, it is an adjustment / relaxation formula, right? And the idea of this formula is very simple. What we are going to do is, in order to assign a cost, we are going to say that if, right? So we are going to write a case if the cost of reaching the source node, right? And what is source? The source can be anything. It can be F, it can be E. It depends on which iteration we are on, which node we are trying to explore. So the source represents that one, and the cost of reaching that source, we are going to say that if this cost plus the weight of the edge, right, the weight of the edge. And what does this weight of edge represents? It represents the distance that it will require to actually go from the source node to the destination node, right? It is going to represent that weight. So let's say I want to reach from A to B, right? Let's say in the first iteration I pick up A and I go from A to B. So what I'm going to do is I'm going to compute the cost of source. So cost of source is 0, right? I'm going to add it to the weight of edge. You can see the weight of edge is 6 here, so I'm going to add 6 here, and I'm going to compare it with the cost of reaching the destination node. And here the destination is the bth node, which is here node B. We know that initially we have assigned that a value of infinity, and 0 plus 6 is less than infinity, right? So 0 plus 6 is less than infinity. So what we are going to do is we are going to adjust, right? That's what this formula represents. If we meet this case, which is the cost of source plus weight of edge is less than the cost of destination, we are going to adjust the cost of the destination. That's why it is known as the adjustment. And relaxation also, because we are relaxing the cost of this B node, right? So it keeps on relaxing when we find a promising node which has a shorter distance than the previous node. That's why it's called relaxing. So what I'm going to do is infinite, I'm going to change this to 6. The similar thing is what I'm going to play out with other neighbor nodes also. I will have to do it with all the nodes. So from A to C the distance is 4, the cost of reaching A is 0, so 0 plus 4 is less than infinity, so relax it to 4. Same thing with D also, because D is also connected, and make sure that it is you are going to follow these directions also, because it is a directed graph. And here we see that 5 plus 0 is 5, 5 is less than infinity, so do the relaxation. Now in the Dijkstra's algorithm, we know that at this step we try to find out the node which is minimum, and we know that we use priority queue to do that. But Bellman Ford algorithm says that don't do that, don't pick any minimum node or that. What you just do is you try to do this relaxation and adjustment to all the edges of this graph, right? So it is an important point. I'm going to write here, do adjustments, and we know to do the adjustment we will use this adjustment formula or the case. So do adjustment for all the edges of the given graph G, right? So the same thing we have done here. Now we are going to follow the same thing with BE also. So from B to E the distance is -1, the cost of reaching B is 6, the distance is -1, and is it less than infinity? Yes, 5 is less than infinity, so I'm going to reassign it to 5. Okay, so now let's take a look at CE, right? So in case of CE, the source is C. What is the cost of reaching the source? 4. What is the edge? Edge is 3. Is it less than 5? Right, so 7 is less than 5. Is it true? No, it is not true. So we are not going to reassign the value of 5, right? Now let's consider EF, and the similar thing is going to play out here also. EF, 5 is the cost, 5 plus 3 is 8, 8 is less than infinity, I'm going to assign it as 8. The last one is DF, right? So in the first iteration you will have to pick up all the edges once, and you will have to do the adjustment using the adjustment formula, right? Very simple. So D has a cost of 5, 5 minus 1 is 4, Is 4 less than 8? Sorry, it's not infinity, it's 8. So is 4 less than 8? Yes, it is less than 8. So do the adjustment, right? So assign 8 as 4. So that's the first iteration. So I'm going to write here that this is actually the first iteration. Right, now you can see that we have done all the adjustments. Now the question is, the values that we have got here, the cost of reaching all of these nodes, which is here, here and here, right? You can see these are the cost of reaching from the source to any of these nodes in the graph, right? Now the thing is that in the first iteration you won't be able to get the shortest distance, right? The whole task is to find the shortest path, the shortest distance. So the Bellman Ford says that in the best case, it may happen that in the very first iteration where you have adjusted these elements once, you may get or may not get the shortest distances. So if it is lucky, it will be able to find out the shortest distance in the very first iteration, but we are interested more in the worst case, right? So I'm going to write here, what is the worst case scenario? How many iterations will it need to find the shortest path, right? So the Bellman Ford algorithm says that it will actually take v minus 1 iterations, right? It will require v minus 1 iterations, and iteration mean that the adjustment of all the edges, right? So how many times you have to do this step that we have done? V minus 1 times. What is v? V is the number of vertices. So here you can see the number of vertices is 6. So it will require 5 iterations. So it means you will have to do it 5 times. In the worst case scenario, you will have to do these adjustments 5 times to be able to get a graph where all the costs are actually going to represent the shortest distance from the source node to the target node, to the destination node, right? So let's move on to the next iteration. Let's see what will happen in the next iteration. So I'm going to write here iteration 2. Okay, so in the next iteration, let's see, now the graph has changed. So we have A here. So instead of writing A, I'm going to write the cost directly here. So cost of reaching A is 0. For B, it is 6. So I'm going to write 6 here. For C, it is 4. For D, it is 5. For E, it is 5. And for F, it is 4. Right, so now you can see the cost has changed. Now it's not infinite, all the nodes have different cost, but still they are not the shortest distances. We are going to again apply the adjustment formula to be able to get the shortest distances, and in the worst case we will have to do it 5 times, right, which is v minus 1 times. So from 0 to 6 the distances will remain same, we are not going to make changes to the distances. So the distance was 6 here, then it was 4 here, and it was 5 here. We are going to adjust the cost, not the distances, and here it will be minus 2. Again it will be minus 2. Here it will be 3 and minus 1. From 5 to 4 it is again minus 1, and from E to F the distance is 3. Okay, so this was the graph that we have got from the first iteration. Let's apply this adjustment on all the edges again. So 0 plus 6, right? So we are actually considering AB here. What is the cost of reaching A? It's 0. What is the distance from A to B? 6. Is 6 less than 6? The answer is not true. So we are not going to adjust this cost. The same thing is with 4 and 5 also. 4 plus 0 is not less than 4. 5 plus 0 not less than 5. So we are not going to adjust it. Let's move on to the CB, right? Let's take a look at CB. What is the cost of reaching C? It is 4. What is the distance from C to B? From C to B, the distance is -2. Is it less than 6? Then the answer is yes, it is less than 6. So I'm going to assign it as 2 here, right? So 4 minus 2 is actually 2. So 2 is less than 6. So 6 will get assigned to 2. Now let's take a look at this one, which is the node D. Now let's take a look at DC here. Cost of reaching D is 5 and the distance from here to here is -2. Is it less than 5? Sorry, is it less than 4? The answer is yes. So 3 is less than 4, which is true. So I'm going to reassign the cost of C as 3. So in this case, you can see that we will have to actually follow an order. We will first do with A, then B, then C, then D. So now the cost of reaching C is actually changed to 3, right? So we have assigned it. Now let's take a look at D and F, right? So D has a cost 5, the distance is -1, so this will also remain unchanged. Now let's take a look at BE, which is here. So what is BE? The cost is 2, it has been changed. So 2 minus 1 is 1. 1 is less than 5, so do the adjustment. So it will now change to 1. Now what we are going to do is we are going to pick up this one, which is CE. The cost of reaching C has changed to 3. 3 plus 3 is not less than 1, so no adjustments. Now let's take a look at EF. 1 plus 3 is 4, again it will be 4. So now we have obtained an iteration to this graph, right? So these are the cost. So now let's move on to the iteration 3. Right, so we will have to keep, the algorithm will keep doing the same steps again and again v-1 times. So we will have to make sure that these steps are followed v-1 times, and you can actually do that yourself also, but I will consider iteration 3 only, and you can try out the iteration 4 and 5 yourself. So A has a cost of 0, B is having the cost 2, C is 3, D has a distance of this cost of 5, then we have 4 here, and then we have 1 here. Okay, so I'm now going to draw all the edges. So these are all the edges of this graph, and the distance to these edges are going to remain same. Now let's assign the distances of these 6, 4, 5, -1, -1, -2, -2, 3 and 3. So this is what the graph. Now the cost, you can see, has changed. One interesting thing to note here is that after this iteration, you can see now the costs are lesser than what it was before, right? It was 6 and 4 here, and now you can see it has decreased. This is why it is known as relaxation, right? So again, we will follow the same steps. 0 plus 6 is 6. 6 is less than 2. The answer is no, so we are not going to change this value. 0 plus 4, again it is not less than 3. 0 plus 5, again it is not less than this, right? Then we have 5 plus 3, sorry, 5 minus 2, which is 3. 3 is again not less than 3. We are not going to change it. Now let's take a look at CB. Here we will see there is an adjustment, because 3 is the cost of reaching the source, which is C, and the distance is -2, and it is less than 2. So if it is less than 2, what we are going to do is we are going to assign it to 1, right? So here we are saying that if the cost of source plus weight of edge is less than this, then I'm going to write here, then assign the cost of destination, the cost of destination will be equal to the cost of source plus weight of the edge, right? I'm writing it in a short form. So that's what we are actually doing here. So it will be adjusted to 1 here. Now let's take a look at BE. Now the cost of reaching B is 1, the distance is -1. Is it less than 1? Yes, 0 is less than 1. Again change it to 0. So you can see that after every adjustment the values are decreasing. It means that the problem is the solution, this algorithm is actually progressing iteration by iteration. It is relaxing the cost whenever it finds a promising node, right? So again we have 0 plus 3 here. 0 plus 3 is less than 4, so it will become 3. So after this iteration you will get a graph which will have these distances, and you can observe that now no more adjustments will change this graph. So this graph G, which we have obtained at the third iteration, so I'm going to call it as G3. So this graph is going to remain same. You will observe that you do more and more adjustments and this graph will not change in iteration 4 and 5. So what does that mean? That means that it is not necessary that you will get the shortest distance in the last iteration or in the first iteration, right? Sometimes there are problems. Sometimes I've seen the graphs which actually uses the Bellman Ford, and the Bellman Ford algorithm is able to get the short distances in the first iteration only, and sometimes it does take the nth number of iterations. Now we have a good idea about this Bellman short algorithm, right? We know how it works, how it does the adjustments. So now we're going to write the algorithm. So first thing is, we know that this we need to follow the steps v minus 1 iterations, 5 iterations. So what I'm going to do here is, in the program I'm going to write a for loop that runs from for I in range 5, because I want to perform some steps. I don't know what are the steps, right? I will write the algorithm here, but I know that I will have to perform those 5 iterations because it is the worst time case, right? Let's move on to the next step, which is I'm going to print here which iteration we are currently on to make a track of all the iterations. Then we are going to create an iterator. So for ITR in graph, now what is graph? Graph is this dictionary here, and here what we are trying to do is we are iterating. This for loop is going to pick up A, B, C, D, E and F. So after each iteration, what we are actually trying to do is we are trying to pick up each and every node. Why we are doing that? Because the adjustments need to be applied to all of the nodes and all of the edges, right? So one for loop is to pick a first element, and again we will create another for loop which is actually going to go inside of that element. So A is actually in the first iteration, this ITR will have a value of A. Then we are going to see that these are actually the neighbors of A. B, C and D are the neighbors of A. So I'm going to write a for loop for neighbor in graph A, right? So ITR is A. So graph of A is going to give me this dictionary here. So now this neighbor is actually going to have value B, C and D. So now we have a way to traverse inside of this dictionary. In a similar way we are traversing inside of this graph. So at every iteration I'm trying to actually pick up each and every edge, right? So the first node will have an edge AB. So first I pick A, then AB, then I pick AC, then I pick AD, and similarly BE, CB, CE and so on. So that's what I'm trying to do, right? So these are two for loops which are required, very important to understand here. First is actually traversing. First is picking up the nodes A, B, C, D, E, F. What you can do is you can also write print ITR inside of this for loop to track that it is actually having the value of A, B, C, D, E, F. Then you can also print the value of neighbor to see this in action, that it is actually going to pick up the neighbors of A and the neighbors of B, C, D, E, F, right? So we are picking up all these edges. Now let's move on to the next step, which is the adjustment formula. So here I'm writing the cost variable, which actually takes this thing is in consideration, which is the cost of source plus weight of edge. So I'm going to make sure that this whole thing is inside a single variable cost, right? So here, what is the cost? Cost is first the cost of reaching the element. We know that element is ITR. So initially in the first iteration, the ITR will be A. So what is the cost of reaching A? I can actually get this by using this dictionary node data. That was the first reason why we created this dictionary node data, so that we can actually make adjustments in the cost and predecessors of this dictionary, right? So first we will assign the cost here by this indices. First you need to give it the node which is ITR, so it is going to pick up A here, and then it will pick up the cost of this. So and then we are going to pick up the edge, right? To pick up the edge, we have this simple index graph ITR. ITR is A, neighbor is going to be B, then after that it will be AC, then AD, right? So what are the cost? 6, 4 and 5. 6 will be added to the cost of reaching A, then 4 will be added to the cost of reaching A, and then similarly 5 also, right? So this is basically the relaxation formula. So now here I'm going to write the adjustment case here, which is if this cost, which is the cost of reaching the source plus the weight of edge, if it is less than the cost of reaching the neighboring node, which is the destination, we know that B, C and D are actually the neighbor. So we are going to calculate what are the cost of reaching the neighbor. So the cost of reaching the neighbor will be picked from this node data, and what will happen, we are going to compare it with the cost of this one. So when we are doing that comparison, we know that if this is true, then we are going to assign the cost of the neighbor, which is the destination, to the cost, which is this one itself, right? So that's why I made sure that instead of writing this formula 2 times, just store the result in just one single variable and you can use it here. Now what is the next step? Next step is we are going to check if the cost of the neighbor of reaching the neighbor is equal to infinite. The reason why we are doing that is we are actually checking, we will have to insert the predecessors also inside of this graph, because we want to know what are the predecessors and how the shortest distance is calculated, right? So if I want to know what is the distance of reaching from A to D, this cost will actually give me that, but the predecessors should also give me what were the nodes that were traversed to reach that distance, right? To get that distance, the shortest distance. So node data, neighbor, cost, infinite, right? This is the first case. So if the neighbor, the cost of the neighbor or the destination is infinite, it means that it has not been explored. So if it is not explored, we are going to simply in the predecessors list, we are simply going to insert the ITR node, right? The predecessors of the ITR. So ITR is the iterator. So what are the predecessors of A, which is here? So what we are doing is we are picking up all the predecessors of the source. So it is actually going to represent the cost and also what are the predecessors of that source node, how that cost was calculated. So that's what we are doing in this line. We are assigning the predecessors of the neighbor equals to all the predecessors of the source node, how you reach the source node, and also what the list of ITR. This list function is actually going to convert this A into a list so that we can append those two lists. That's how we are going to do the concatenation. So we are going to concatenate that node here, right? So whenever we want to calculate the cost, we can do that. But if you want to know the predecessors, this step is optional. If you don't want to know the predecessors, you can skip this step, but this is a very useful line. And what you can do here is, here you can try to print the, so here we have another else part also. What will happen if the predecessors, what will happen if the cost of the neighbor is not infinite? So if it is not infinite, it means that it has been explored before, it has its set of predecessors. But since we have a more promising cost, we have a more promising shortest distance, we also have a much better path and a set of predecessors that can give a better cost. So what we are going to do is we are going to clear off all the predecessors of the neighbor or the destination node, right? Because we have a new cost and we have a new set of predecessors. So how will we insert the predecessors? We are going to do the same thing. We first empty the predecessors list and then we add the node data ITR to the predecessors list, right? All the predecessors of the source will get inserted in the predecessor of the destination, and we are also going to insert the node that we are currently at, right, which is the source node. So source node with its predecessors is going to get inserted inside the destination predecessors. So if you want to take a track of how the predecessors and cost are changing, I will print node data here. So you will be able to see the dictionary at each and every iteration, how the dictionary is changing. And now you can print the shortest distance, because now the algorithm will go 5 times, it will go through all these iterations, changing the cost, the predecessors, and now after all the iterations we are going to print the node data, and after all the iterations the costs have been adjusted and relaxed. So now we can get the shortest distance by just converting the node data destination cost. So destination is actually you can pick any element. I have, in this case I have actually picked up E here, so destination is E. So if I want to find out the cost of reaching E, node data E is here and the cost is what I can get here. So I will just convert it into string to print that out, right? Similar thing I am going to do with the predecessors also. So if I want to find the shortest path, I will convert the same thing into string. I will just take the predecessors of the destination and I will also add the list of destination, which is the destination itself. So the destination is also inserted here. So this is the whole program and this is the whole explanation, and you can actually try it out yourself. You can program this yourself and you can see how the things are done here and how it is corresponding to these cases. The predecessors part, which is here, these 6 lines are important. It will give you the shortest path and it is optional also, but it is good that if you are able to understand how these 6 lines are working. Now let's try to actually run this program and let's take a look at the results of it, right? So here I am going to clear this off and I am going to run the command python3 bellman4.py. So here you can see in the iteration 0, the cost of A has been assigned to 0. There are no predecessors of A. B, you can see the cost has assigned to 2. So you can see here in iteration 1, the B has a cost of 2. The predecessors are A and C. So it means that the cost of reaching B is 2. And how do you reach this cost, right? How do you reach this? You reach this through AC, right? So you can see that if you go from A to C, you are actually going to get this cost too, right? What is the cost of reaching C? It is 3. And how are you going to reach? You are going to reach through A and D, right? So you first go from A to D, then D to C, and you will get this cost C, which is 3 here. Similarly, it is going to play out for iteration 0, 1, 2, 3, 4. Now interestingly, you can see here at iteration 3, cost is of A is 0. It is 1 for the B. The predecessors are A, D, C. Here in the iteration 4 also it is same. So this, I think this whole thing is actually same as iteration 4. So it means that in the iteration 3rd only I was able to get the required result, right? So what is the shortest distance from, you can see it is showing 0 here, and it is correct also, because if we want to reach from A to E here, right, the destination is E. So you can see in this diagram E is here, so the distance is 0, so it means that the result is correct here, our program is correct. The shortest distance from A to E is 0, but how are we going to reach that? The answer is here. Shortest path says that the path is from A to D to C to B to E, right? So let's take a look at this one here. So A to D is a distance of 5, which is correct. Then from D to C, the distance is -2, so the total distance is 3. Then from C to B, because you can see here, now it's C to B, so 3 minus 2 is 1. And then finally from B to E, right? So B to is actually 1 minus 1, which is 0. So this is a very interesting program, and this is what I've actually written here, and this is a very important thing. And now we are going to end this tutorial. In the next tutorial we are also going to make some adjustment, write some extra lines to understand when we are going to meet a negative cycle, and when we reach a negative cycle we are going to report that, and the program will automatically report that there is a negative cycle. In this case there was no negative cycle, but there will be cases when there are negative cycles. So negative cycles basically means that you have a cycle in a graph. Let's say you have a graph which has the nodes 1, 2 and 3, and they're forming a cycle, right? Let's say they are forming this cycle. The cost of all the edges, let's say the cost is -10, then 1 and 2 here. If the sum of all the cost, which will be here 10 plus -10 plus 2 plus 1, which will be -7. So if it comes out to be negative, we call it as a negative cycle, and Bellman Ford algorithm fails at the negative cycles, but is also used to actually report that, right? It will report that, and we will see that in the next tutorial. So basically that's all for this tutorial. If you have liked my efforts, make sure to subscribe my channel and also like this video. It helps the algorithm to reach more students, and it helps a lot of other people also. So that's all for this tutorial. Thanks for watching.